Okay, this video basically capture few important information about capacitors. So, okay, so so, so during circuit analysis one, you may basically when through this basics of capacitors. So what I want to highlight in this video is like so we basically model the behavior of the capacitor. So behavior means how this capacitor act against the voltage we apply and how it's induced the current. So this modeling is basically capture the voltage, the relationship between the voltage and the current when we have a kind of a capacitor in a circuit. So we know that for any given capacitor, if we apply external voltage, so we know that the induced or the stored charge of the capacitor can be given by this equation CV. So Q is the stored energy or stored charge of the capacitor. So if you have a capacitor like this, and if you apply a kind of a voltage across this capacitor, so the capacitance of the capacitor is in C. So this is C farad. So then the stored energy between these two plates is given by Q. So Q is actually proportional to the voltage we apply across the voltage. So if we increase the voltage, so the amount of charge accumulate between these two plates is simply increasing. So we basically rewrite this equation in a precise way like this: Q T equals CVT. So in this circuit analysis 2 module, we basically consider time varying voltages and currents. So we know that if you denote voltage by capital V or current by capital I, this basically represent the DC quantities. These are DC quantities. So if you simply with a simple V or simple I, these are kind of AC quantities. So these are random quantities. So these are kind of fixed values. So if you use capital V or capital I, it basically represent the DC quantity, which is a kind of a constant along with the time. So it's not depend on the time. So if you use simple V or simple I, it's basically kind of a random quantity. So this is kind of a random quantity. So random quantity means, so this whatever the voltage or current is depends on time. For most of the time it depends on time. So whatever the voltages current which we discuss here, a function of time. So that's why we come up with this kind of a notation, Vt and It. So it means like this, in this case V is a kind of a random voltage which depends on the current, or which is a function of time, sorry, which is depend on time, which is a function of time. So here also this I represent a kind of a random current which depends on time. So I is a function of time. So likewise for this case also we can introduce this time dependency here. So now this Q becomes Qt. So it means the this is actually the stored charge at a given time t equals to the capacitance of the capacitor, so which is measured in farad, and the voltage across the capacitor at any given time t. So this is basically with respect to time t. So this is the stored energy or stored charge of the capacitor at any given time t equals to C times the voltage at that time. So whatever the voltage appear across these two terminals at a given time t. So this can, so then from this one we can like so if we differentiate this one with respect to time, what happens to this? So this becomes qt equals c is a constant, so we can treat it as a constant which is independent of time and bring this c out from this differentiator. So c here and d over dt vt. So now what happens to this one? So we can further simplify this. You know that this dqt over dt, or the rate of charge, is actually represented by the current. So the current is actually the rate of charge. So this is I equals C times the derivative of the voltage. So this is actually this. So if we have a capacitor having a capacitance of C farad, so if you apply a time varying voltage across this capacitor, the induced current or the current flow through the capacitor at any given time t is simply the product of the capacitance and the derivative of the voltage. So this is actually derivative of the voltage Vt. So it's not proportional to the voltage. So the induced current is basically proportional to the derivative of the voltage. So this IT, which is the induced current across this capacitor, is proportional to the derivative of the voltage, not for the voltage. Okay, so we'll take a simple example. So now, so this is the time. So this is the voltage we apply across this capacitor. So this is the voltage we apply across this capacitor. Okay, what about the induced current? So what about the induced current here? So this is the relationship, so we can stick into this relationship. So this is the fundamental equation which describes the behavior of the capacitor, so you can keep in mind. So the induced current across the capacitor is simply C times the derivative of the voltage. So now we need to evaluate the derivative of the voltage to get this current. So for example, so we'll assume that C is actually 1 farad for the moment. So now then the induced current is actually exactly equals to the derivative of the voltage. So between 0 and t naught, so the derivative is actually, so this is a kind of a linear trend. So the derivative means the gradient of this linear trend, so which is actually a kind of a constant. So the gradient is constant. So this is t naught. So the current is a constant. So the gradient is actually 1 over t naught. So from t naught onwards, so we have a kind of a fixed voltage. So then the derivative would be 0 because so Vt becomes a constant voltage of 1 volt. So then the derivative of the constant would be simply 0. So from here onwards, the induced current is 0. So this is the variation of or the induced current across the capacitor. So during this ramp, you have a kind of a constant current flow through the capacitor. So once this voltage converges to 1 volt, so you don't see any current flow through the capacitor. So this is a very simple example. How do we get the induced current of a capacitor when you are given a voltage variation? So it means if you are given this quantity, how do you get this? So this small simple example is explain the way we can get the induced current across the capacitor when you are given the voltage variation or the voltage fluctuation across the capacitor. So from this we can take two conclusions. So according to this definition, we know that the induced current is equals to C times the derivative of the voltage. Okay. What happens when this voltage is a fixed constant value or a kind of a DC value? So if you are given a fixed DC voltage across the capacitor, what's the induced current? So from this basic definition, if Vt is a kind of a constant, derivative of the constant becomes 0. So then the induced current is actually 0 because the derivative would be 0. If the voltage is a kind of a constant, so the derivative of the voltage is 0, so then the induced current should be definitely 0. So it means if you are applying a DC voltage, so you can't see any induced current across the capacitor. So it means if you have a capacitor, you can't see any current flow through the capacitor. So then capacitor can be replaced using a kind of open circuit. Because this I or the current flow through the capacitor is 0 means we can basically replace the capacitor. When we apply a DC source, we can simply replace the capacitor with an open circuit element. Okay, so the second, what happens? Okay, so let's think about a kind of a situation like this. So the voltage is something like that. So voltage is something like that. At any given time, this voltage is simply raised to a kind of a certain value during that period, during this rising edge. What about the gradient of the voltage? So if you simply consider a kind of a rising edge of a voltage, so this is your voltage function, so you have this kind of a rising edge, so immediately jump into different level. So if it is a rising edge, what happens to the derivative of the voltage? So the here the gradient is infinite. So that it means like derivative is the angle between the horizontal line. Now it's become 90 degrees. So this basically equals to this converge to goes to infinity. So then the induced current would be mathematically infinite, because this the derivative becomes infinite, and c times the derivative or c times the infinity again gives the infinity. So then it means once you have this kind of a variation in your voltage, so your current ideally increase to infinity. But in practical scenario, you cannot increase or you cannot boost your current to infinity, because see, whatever the circuits you connect, this capacitors are powered by the fixed DC sources. So there's a limit for the current, so they cannot absorb infinite current from the source. So there is a maximum current which particular circuit can draw from these external sources. So it means at this point, so you can see a kind of this current goes to I max. So the whatever the maximum current which we can draw from the source is Imax. So for during this period, so the current is actually immediately jumps is to maximum. So for this kind of a scenario, so if you plot this, it's something like that. So during this, no voltage appear across the capacitor, so the derivative becomes zero. So the derivative becomes zero. Again, during this period, the applied voltage is a constant value. So then again the derivative becomes 0. So from here onwards also derivative becomes 0 and the induced current is 0. But at this point at t naught, so at t naught, so it jumps from 0 to this fixed value. So the during this rising edge at t equals t naught, there's a infinite current drawn from the circuit. So we can modify this. So here we have a spike, kind of a jump up to I max. T naught. So he simply draw it like this. Okay, it's something like jump it down. So it jumps to I max at t equals t naught and again immediately back it to 0. So if you have this kind of a rising edges, ideally your current induced across the capacitor would be infinite, but it's not practical. So then this at these kind of edges, your current jumps to its maximum and immediately drop it to the 0 for this case. So then this is kind of a harmful for the capacitors. So we believe like these capacitors cannot handle this kind of rapid variations. So ideally for this kind of infinite gradient situation, so this during sharp rising or falling edges, sharp rising or falling edges, so you can see this induced current would be mathematically infinite. But in practical situation, it never goes to infinity, but it basically absorbs the maximum current which can run from the external source. So then you can observe kind of a spike at this particular rising and falling edges. So as a convention, so we basically assume that these kind of rapid changes cannot be handled by the capacitors. So these kind of abrupt or instantaneous in voltage across the capacitor is not possible because it leads to an infinite current flow through the capacitor. Ideally, whatever the circuit should be completely burned due to this heavy current. So we basically assume that this capacitor cannot handle this kind of rapid changes of voltage. So all the time capacitor can manage this kind of a smooth variations. So this kind of a smooth variation, not this kind of rapid changes. Okay, so we basically identify a couple of key points. Okay, couple of key points. So this is one. Okay, so this is actually this is actually the fundamental equation for the capacitor. The induced current across the capacitor is E times the derivative of the voltage. So this is not aligning with Ohm's law. Ohm's law is actually current is proportional to the voltage, but in this case current is not proportional to the voltage. Current is proportional to the derivative of the voltage. So this is the very fundamental equation. From this fundamental equation, we conclude get a one conclusion. If this voltage across the capacitor is a kind of a constant, so the induced current would be zero, and we can simply replace the capacitor with open circuit element. So because the derivative of a constant would be zero, so then it means like if you apply DC voltage across the capacitor in a circuit, you can replace the capacitor with the open circuit element and model the behavior. So then there won't be any capacitor in the circuit. There's an open circuit element once you apply a DC voltage. So again, if you have this kind of sharp rising or falling edges, so then the derivative becomes infinite and you will see a kind of an infinite current idea. In practical circuit, at the given point, if you have this kind of a rising or falling edge, so then the current is simply goes to its maximum current, which we can draw from the external source. So then we identify that capacitors cannot handle this kind of a rapid or sharp edges in the voltage because it basically gives the infinite current. Okay, this is the very basic of the capacitor. So okay, so then we identify one we basically identify the relationship between the voltage and the current across the capacitor. This is the relationship I because C times the voltage, the derivative of the voltage. So from this we can simply obtain the expression for the voltage by integrating this. First we multiply this current with this cross multiply this current and the derivative, and we can take the integral. So it becomes 1 over C integral it dt. So if you want to make it a kind of a finite integral, so we can add this. So dt. So this becomes a kind of a finite integral. So 1 over C integral it dt gives the voltage across the capacitor at any given time. So if you make it a kind of a finite integral or definite integral having this proper limits, so we can assume that this integral would be a kind of integration from minus infinity to t. So so what is actually minus infinity and t? So let's think about the time axis. So this is t equals 0. So t equals 0 means actually for this circuit analysis we assume that t equals 0 gives the present condition. So t equals 0 gives the present condition. So whatever the values appear as positives up to the positive infinity is considered as future conditions. So whatever the negative values up to minus infinity simply represent the past conditions. So it means this basically considered, so this integral can be split into two. 1 over c minus infinity to 0 I tau d tau plus 1 over c 0 to t. Okay, so then why we use tau here? This is again a kind of a random variable like t. Why we put tau is actually the upper limit of this integral is a kind of a random quantity. So this is a random quantity. So once you integrate this expression and substitute t, so then it would be fine. But the problem is if you put like this, so whatever the outcome of this product is a kind of a function of t. So then you can't substitute this t with this t, so it's kind of a misleading. So that's why we put another variable which is very similar to t. So then if it is the case, if this is the case, if you have tau here, so then this become I tau d tau. So then this function become a expression of tau, then we can simply replace this tau with t. So that's why we put tau here, nothing else. Okay, yes, then so this integral, this t goes from minus infinity to 0 means this basically represent the past condition. Okay, so this basically gives a past condition. This is covering the future because this integral goes from 0 to t. T is a kind of value greater than 0. So then this basically gives the um, future condition. So this past condition we can simply capture it as this is this 1 over c, this integral gives a kind of a voltage because this is equals to the voltage. So this is actually equals to the voltage. So then we can simply say that this is the voltage at t equals 0. So this is, in this discussion we as treat this as the initial condition of the capacitor. So this is the initial condition, the capacitor. So the voltage at t equals 0. So the voltage at t equals 0 means whatever the voltages induced across the capacitor should from minus infinity to 0 is simply absorbed to this initial condition. Whatever the variation is simply em- embedded inside this V0. So this is the initial voltage of the capacitor at t equals 0. So then from t equals 0 to t equals t, we basically capture the voltage variation through this integral. So then from this we can get this kind of equation. 1 over c 0 to t I tau d tau plus vc. So this is actually a kind of equation which is basically gives the induced or the applied voltage across the capacitor. This is equals to 1 over c. C is the capacitance of the capacitor, and then integration of 0 to t current, and here you have this initial condition. So keep in mind, without this initial condition you will never get an exact expression for the applied voltage. All the time keep in mind this should be there, this should be there. So if you whatever the problem is, simply say that your initial condition is 0, so you can simply uh, evaluate the voltage as 1 over c integral of current. Otherwise you have, all the time you have to consider this initial condition. Either you have to calculate it through the circuit, or else you can get the value given in the question. So keep in mind, if you want to evaluate the voltage across the capacitor, in addition to this integral you have this initial condition as well. So this is very simple. Like if you are like replacing an indefinite integral. Indefinite integral means so integration without a proper limits. So you simply add a kind of a known constant to the integral formula. So likewise, so we have this initial condition which basically capture the initial state of the capacitor. So we have to, so we should keep in mind, so either you have to calculate this initial condition, or else you have to plug the value given in the question. Otherwise the question should clearly mention that your initial condition should be 0. So this the if you want to evaluate the voltage across the capacitor, keep in mind that there is a term come from the initial conditions as well. So then we basically uh, identify two equation. This is one, current is equals to C times the derivative of the voltage. So the second is, if you want to evaluate the voltage across the capacitor, this is equals to integral of this current plus the initial condition of the voltage. So this is initial condition of the capacitor. Okay. So we'll go through one example. So I am referring exercise 1 ex1 in the slides. So it gives that, so we have a capacitor of capacitance C is given as 400 microfarad. So and it is given that this is the voltage appear across the capacitor. So it's a kind of a piecewise continuous function. So in between minus 10 to minus 2 there's a kind of a linear trend with a negative gradient. Then from minus 2 seconds to 0 we have a positive gradient. Then we have a kind of a sinusoidal type function, and then triangular type of behavior. So Okay, during this 0 to 6 seconds, so between 0 second and 6 second, the voltage is simply behaves as a kind of a parabolic function. So it's like 6t minus t square. T times 6 minus t means, so this is actually 6t minus t square. So otherwise the rest of the trends are very similar to the linear trends. Either it's has a positive gradient or negative gradient depending on the uh, time span. So you are asked to evaluate the current at given certain given time. So you have to find the current at t equals -4, -1, 1, 5, 9. So very simple. So this is the relationship between current and voltage across the capacitor. C times the derivative of the voltage. So to evaluate this derivative, Vt should be described in a mathematical function. So this is the ideal way of doing that. So if it is a linear constant behavior, so it's easy because you need to evaluate the gradient. So the derivative itself gives the gradient of the function. So otherwise you have to model this behavior using a mathematical formula, mathematical function. So we know that between -10 to -2 we have a linear trend with a negative gradient. -2 to 0 again we have a linear trend with a positive gradient. So in between 0 and 6 we know the function Vt, which is t times 6 minus t. So from 6 to 8 again a positive gradient with a linear trend, and 8 to 10 we have a kind of a negative gradient with a linear trend. So if you want to evaluate the current at t equals -4, so we know that t equals -4 happens in between -10 to -2. So if you just draw a line between, so this is the trend. So we have -10, -2. So this is the trend. Here this is -10. So we can simply evaluate the gradient. Okay. So this is actually, so the derivative is equal to minus this height -10. So this is actually 10 divided by 8. So this is the current. So if you multiply it with C or the 400 microfarad, it gives the current. So this current is actually 400 microfarad into -10. Wait. So it basically gives -0.5 milliamperes. So if you want to find the current at t equals 1, so t equals 1, if you want to find the current at t equals 1, we know that the trend between 0 and 6, this is 1, is actually Vt is given by t times 6 minus t. So it means like you need to evaluate the derivative at t equals 1, means ideally you have to evaluate the derivative at this point. So you have to evaluate the derivative at this point. So again, if you know this function Vt, you can simply evaluate the derivative function. So it is 66 minus 2t. So this basically gives the derivative between 6. So this expression, because see that you have a t here, so it means with the value of t you have different derivatives. So once you substitute 0, so you can simply get the derivative at 0 point. So if you submit t equals 1, you can get the derivative at t equals 1. If you just substitute t equals 5, you can get the derivative at t equals 5 likewise. So this is a kind of a derivative, also kind of a time dependent function. So this generally gives the gradient or the derivative variation in between 0 and 6 seconds. So if you want to evaluate the derivative at any particular time, so you need to evaluate this. So you need to take the derivative at t equals 1. So then just substitute t equals 1 here. 6 minus 2 gives 4. So this gives the derivative at t equals 1. So then it equals c for 100 microfarad into the derivative at t equals 1. So which is equals to 4. So this is 1.6 milliampere. So rest of the currents can be easily found. So the simple idea here is, you know the expression. So you know the expression. So you know the expression between the current and voltage for the capacitor. So then keep in mind all the time you need to find the derivative of the voltage. So then anyhow you need to make it mathematically. So if you can explain the behavior of the voltage function at any given time using a mathematical function, then you can easily evaluate the derivative or the d over dt value and just plug it to the standard equation and obtain the current. So it's very simple. So only thing is, like, you need to find a mathematical function to represent the behavior of the voltage. So then it's easy to evaluate the derivative. So I just give actually simple examples how to evaluate the current when the trend is linear, and how to evaluate the current when the trend is not linear but mathematically defined. So this is a very simple example. So then again, so I'll explain one more example. So you can refer this exercise number 3 in the slide. So you are given a kind of a circuit having a source. So the source is actually 3 sine 2t. So the your voltage source is actually 3 sine 2t. It's the voltage source which powered the circuit. So we have 3 series capacitors. So how do you manage to evaluate the current? So so you are asked to evaluate the voltage across the first capacitor. So you are asked to evaluate the voltage across the first capacitor, and it says that the initial condition of the first capacitor equals 10 volt. So how do you approach it? So we know that this is the relationship between the voltage and the capacitor the voltage and the current across the capacitor. So if you want to evaluate the voltage across the capacitor, so we know that this is the relationship 1 over C integral plus the initial condition. So for this, if you think of like capacitor 1, cap number 1, so this becomes V1t equals 1 over C1, its capacitance 0 to t. So the current flow through the capacitor and the initial condition of the capacitor 1. So this is given, so this is actually 10 volt, so you don't need to worry. So this is also given, this is actually 1 farad. So we need to find this current flow through the capacitor 1. So by looking at the circuit, we can simply say that the current flow through the capacitor 1 is similar to the current flow through the capacitor 2 and 3 because they are connected in series. So then we can simplify the circuit by combining the series capacitors into a single equivalent capacitor. So we know that if these capacitors are in series, so you can evaluate the equivalent capacitor. So the equivalent capacitance from this is actually 1 over C equivalent equals 1 over 1 plus 1 over 2 plus 1 over 2. Okay. So then this is equals to 2 and C equivalent would be half farad. So then you can simplify the circuit like this. You have a source and this is actually C equivalent, which is equals to half farad. So this is the current flow through the capacitors. So you can evaluate this current. So this is the I current flow through the capacitor equals half farad. So the derivative of the voltage 3 sine 2t. So it is equals to 3 sine become cosine 2t into 2. So then this is equals to 3 cos 2t. So this is the total the current flow through the capacitor. So if you apply voltage across the series set of capacitors in a way of 3 sine 2t, so you can simply get the current as a cosine, because you know that sine function gets differentiate with respect to t, it becomes a cosine. So then this is right. So you have a tradition of current flow through the capacitor. Uh, so you can have a kind of a, so this is the current flow through the capacitor. So 3 times cos 2t. So then, so we know that this same current flows through the entire circuit. So this is the current flow through the 1 farad capacitor, 2 farad capacitors as well. So then we can easily plug it into here. So V1t equals 1 over C1. C1 is 1 farad. 0 to t. The current flow through the capacitor 1 is 3 cos 2t. So we will put down d tau plus 10 volt. So then this is equals to 302 sine 2t plus 10. So this is the voltage variation across this capacitor 1. So 3 over 2 sine 2t plus 10. So keep in mind, so if you simply ignore this initial condition, so your voltage across the capacitor would be this. Okay, so this never capture the exact voltage variation across the capacitor, because for example if you plot this one 3 sine, so this is something like that. So this is like 3 over 2, and here it's like minus 3 over 2. But with this initial condition, this is something like that. So here it's 10, this is 11.5, this is like 8.5. So this is the exact voltage across the capacitor 1. So if you simply ignore this initial condition, you can't get this kind of a trend at the end. So keep in mind, so you have to consider the initial condition as well. So go through this series and parallel capacitance. So how do you get the equivalent capacitance for the series and parallel scenarios, and then apply those concepts to simplify a circuit, and then this is the very fundamental equation you need to keep in mind. So during this entire discussion we want this equation and this equation only. So if you know these two, you can manage any circuit with a capacitor. So hope this basics give a kind of a clear idea about the circuits having capacitors. So we'll discuss this charging and discharging effect separately once we move to the first order circuit. So until that, this uh, simple concept should be enough, more than enough, to manage a circuit with capacitors.